Morning, good afternoon, wherever you may be in your day. Thank you as always for choosing that chemistry part of your day. So today we're going to introduce the concept of molarity, do a sample calculation with it, and this will really spill over and go hand in hand with some solution making calculations that use the concept of molarity. So let's get started. And as a couple quick reminders, so we're going to use molarity to convert between amount and volume. And remember, our unit of amount in chemistry is the little thing that digs in your yard, the mole. And we can, of course, use our formula weight then to go from moles to grams, or vice versa. And we're going to use molarity likewise as a conversion factor between amount, which is moles, which is really what we care about in chemistry, and volume. And standard volume would be liters, but typically, if we're talking about a lab or a practical situation, we might be talking about milliliters and have to do an additional conversion there. So let's get started. Anytime we do a new idea, let's start with a couple definitions. So let's start with molarity itself. Our symbol would be the capital M, would be a big M, and it is defined as the moles of solute per liter of solution. So it's the number of moles in every liter of solution. This does lead into the question of what's a solute, what's a solution, which is a good question. So let's go with that. And we're going to go way back to chapter 1. A solution is a homogeneous mixture. Now I know a homogeneous mixture when I see one because it looks clear. I can see through it. And that's typically liquids or gases. These are things that can flow and mix well together. So mixture of more than one thing. The thing that we have the most of, the majority, and there can only be one majority. It's the majority. That's the solvent. Now what we have less of is the solute. So it's in the minority. And you can have more than one minority. You can have more than one minority group in the US or in a country, and same thing in a solution. So an example of something I can see through that looks clear is the air between my eyes and the camera. So let's take the air. What's the major component or the solvent in the air? We would say the major component is, very good, nitrogen. And what are some of the minor components? Well, we have oxygen, carbon dioxide, water vapor, hydrogen, neon, etc., etc. Methane, probably not huge amounts of these things, but trace amounts. So we can have a lot of solutes, but only one solvent. And usually you talk about solutes being dissolved in solvents. So if you were to really describe the air, the simplest description of it would be oxygen dissolved in nitrogen, with trace amounts of the other things. If we took the ocean and we filtered it so it was a nice clear, we got to get the fish out. Fish would leave it as a homogeneous mixture. So get the fish, algae, that kind of stuff out, and take some nice clean ocean water. It'd be the same idea. Most people, the simplest way to describe the ocean would be salt dissolved in water. But we're in chemistry class, we can do a little better, so we can at least say sodium chloride. And even beyond that, there's all kinds of trace particles in there. There's magnesium chloride. There's a little bit of calcium carbonate. There's all these different compounds that are in there, which is why they say sea salt's better than processed salt. You get these trace nutrients in there as well as the salt that you want on your French fries or whatever else you're eating to have that salty taste. And really anything the ocean touches will dissolve at least a little trace amount into it. So there are many, 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 many solutes. But there's only one solvent, and the solute is dissolved in the solvent. There we go. We got our vocabulary. Let's do some math. I know you're itching to do it by now. All right, let's take a very straightforward problem. A 100 milliliter solution is made by adding 10 grams of magnesium perchlorate to a sufficient amount of water. What is the molarity of magnesium perchlorate in such a solution? Okay, so always we want to work backwards. We're looking for the molarity of magnesium perchlorate. Notice I put it in words, so let's do a little practice. Magnesium is Mg. Perchlorate is, I see that ATE, that means polyatomic. Cl and ATE means Cl's and O's. Then I got to memorize that per gives me 4. Now we go into the charge. Chlorine, odd numbered element, far right of the periodic table, tends to have small charge, -1. Magnesium is in family 2, +1, +2. We do our cross down, and we get the empirical formula, not the molecule, but the empirical formula for magnesium perchlorate is as follows. 1 magnesium ion per every 2 perchlorates. All right, so now we know what we're looking for. We want to know the molarity, so we got to remember always put the big M, and if you're in class, you're going to hear me say blank per blank. I don't really want you to use molarity when you do calculations. I want you to think of the component parts, blank per blank. So in this case, it's going to be moles per liter. And more specifically, it's going to be moles of that magnesium perchlorate per liter. And we don't, usually we state it, it's number of moles per 1 liter, but if we can get the number of moles per any number of liters, take the ratio, we have our answer. So we really need to do 2 calculations. How many moles of magnesium perchlorate do we have, and how many liters of solution? So we can start either way. I'm a creature of habit, so I'm going to start at the top. Moles of magnesium perchlorate. Do we have any number up here that says moles of magnesium perchlorate? No, that's typical. But do we have a number related to magnesium perchlorate? The answer is yes. That's grams. Grams is a unit of mass. Can we relate mass in moles, grams in amount, mass in amount? Absolutely, that's our formula weight. So we have to go to our old friend, the periodic table. I chunked it out. Magnesium is 24.31. Chlorine is 35.453, and oxygen 16. If we take 1 magnesium, 2 chlorines, and 2 times 4, 8 oxygens, we add it up, we get 223.22 grams per mole. So now we just take our grams, and hopefully this is getting comfortable by this point. Divide by our formula weight. Notice I'm putting the chemicals in there. Don't get lazy on me. If I can do it, you guys can do it. And we just calculate that through. And if you look, we have 3 significant figures here, so our answer should have 3. And I get 0.0448 moles of magnesium perchlorate. So we've done half the problem. We have the number of moles. Now we need to find the number of liters of solution. Well, liters is a unit of volume. Let's see. We have milliliters of solution. That's pretty good. So likewise, and I hope you guys are getting in this habit. Notice I'm doing the railroad tracks. These are straightforward calculations, but I'm still using the same methodology. Milliliters is on top. I'm going to cancel out with milliliters on the bottom. We want liters. So I'm going to put that on top, and it takes a whole bunch of milliliters. They're pretty small to equal 1 liter. So it's 1,000 to 1. 100 divided by 1,000. And I get 0.1000 liters. Divide those 2 numbers, and I'm left with my answer, which, if I've done this correctly, I hope, is 0.448 molar magnesium perchlorate. And that should be our answer. This is a reasonable number. Just to give you a feel for these things, molarities can run really, really small. You could have 10 to the minus 6 molar, micromolar, for example, or even nanomolar in some cases. And the top largest molarity you can really have is probably about 15 to 20. Anything bigger than 20, I can guarantee you it's wrong. And quite frankly, if you're in the 15 range, it's probably too high too. Even though those exist, pretty rare to ask you to do a calculation that way. I want to take this problem one step further. Change the wording on you just a smidge. And say, what would be the concentration of each ion? Or what if I had asked the exact same question, but I said, what was the concentration of magnesium ion at the end? Or perchlorate ion at the end? Maybe we don't care about the magnesium. It's a nutrient. It's good for us. Maybe the perchlorate we're worried about, that's bad for the environment. We want to know how much that's being released, for example, if we spilt that much. Okay, so we have to relate the salt itself, which is dissolved in water, so we'd call that aqueous, to its component ions. And if we look at this, and a lot of times I like to think about this, not the greatest example, but, or at least a little morbid, is kind of cut the head off, cut the metal off, everything else stays behind. So we get an Mg. And think about when we took the names to the symbols. Our symbol was magnesium. Our symbol was perchlorate. AQ, remember, means dissolved in water, or aqueous. And then this is not quite right because we haven't balanced our equation. We have 2 over here, so we'd have 2 here. I'm going to put those there and emphasize it. We don't need the 1, but I want to emphasize it for our calculation. So, a lot of times, chemists, instead of saying what's the concentration or molarity, they'll put these little brackets. These brackets mean molarity. So it's concentration and molarity whenever you see these brackets. So this would be the concentration of perchlorate, concentration of magnesium. So if we look at this, every 1 magnesium perchlorate salt also gives me 1 magnesium ion. So this is easy. This is still the same number. 0.448 molarity. If we look at perchlorate, though, this is going to be something entirely different. Every 1 magnesium perchlorate gives us 2 perchlorate. So really what we would like to do is mathematically represent that. And what we really want to say is that every time we use a mole of our salt, salt being generic for ionic compound, we get 2 moles, or 2 units, of ClO4-. Pretty straightforward calculation, but you could do this with any of these, what we call stoichiometric coefficients, or any of these coefficients, you could bring them down to the same thing. And now hopefully you're starting to see why I want you to write what chemical's behind every time, because this, although they're both moles, they don't cancel out, and one needs to be in the right place to do these calculations right. So now it's pretty straightforward. 0.896 molarity, and we are done. And as always, thank you so much for your time and attention, and hope this was enlightening.